Hi everyone. Today I want to discuss what space engineering teaches us about software design. As we know, quite often globally we have accepted that we don't know everything about space. In fact, there is probably so much more that we haven't explored than what we do know so far. And that teaches us a lot in terms of a mindset when it comes to exploration and optimization. However, on Earth, sometimes we do treat things differently, especially when it comes to global systems. And I thought it's a really good comparison to make and see how those two mindsets actually in a sense, could contradict each other, and that space engineering has already optimized and, in fact, has created its entire structure around the unknown about things that we cannot predict. And therefore has optimized for it. So, for example, when a spacecraft leaves Earth, it enters a domain where deterministic assumptions collapse. Signal propagation is delayed by physics. Sensor readings contain noise. Orbital mechanics operate under continuous perturbation. Radiation introduces bit flips, and mechanical stress accumulates unpredictably. So we know that nothing in that environment is perfectly stable, and yet missions do succeed, not because uncertainty is removed, but because it is modeled, bounded, and engineered around. So space engineering begins with a simple premise. The system will operate under incomplete information, and that premise is equally true for modern software. In orbit, telemetry is not optional. Every subsystem continuously emits state, thermal gradients, power consumption, orientation, vectors, actuator response. These signals are not collected for curiosity, they are collected because control requires feedback. In control theory, a system without feedback is unstable. Software systems are no different. Logs are historical state transitions. Metrics are aggregated system behavior. Distributed tracing reconstructs causality across nodes. So without observability, a distributed system degrades into guesswork. Space engineering treats observability as a structural requirement. Software engineering often treats it as instrumentation added after deployment. And that distinction matters. Another fundamental principle in space systems is fault tolerance. Critical subsystems are not singular. They are redundant, sometimes triply redundant, and this is not inefficiency. It is risk mitigation under high consequence. In distributed software systems, the same pattern appears. Replication across nodes, later election under partition conditions. Retry logic for transient failures. And the key insight is this: failure is not an edge case. It is a steady state condition in large systems. Space engineering formalizes this through failure mode and effect analysis, as short for FMEA. Every component is evaluated not only for function, but for failure behavior. Software architecture benefits from the same rigor. What happens when a dependency times out? What happens when a cache becomes inconsistent? What happens under partial network partition? These are not operational concerns, they are architectural ones. Space missions are also deeply probabilistic. Trajectory corrections account for drift. Sensor fusion reconciles noisy inputs. Kalman filters estimate state under uncertainty. The system never has perfect knowledge of its own position. It does estimate. Modern distributed systems operate similarly. Eventual consistency acknowledges the global state cannot be instantaneously synchronized. Consensus protocols balance latency against agreement guarantees. Load balancers distribute traffic under variable demand. We already design probabilistic systems. We just don't always acknowledge that we do. Space engineering makes that explicit. There is also a temporal dimension. Space missions are designed for long operational horizons. Components must survive thermal cycling, radiation exposure, and mechanical fatigue. This creates a bias toward conservative design. Extensive simulation precedes deployment. Edge cases are rehearsed. Failure is injected deliberately in testing environments. In software, we're beginning to adopt similar practices. Chaos engineering introduces controlled failure. Stress testing explores nonlinear load behavior. Threat modeling anticipates adversarial input. These practices are not pessimistic. They are acknowledgments that complex systems behave unpredictably at scale. Perhaps the most transferable lesson is cultural. Space engineering does not treat uncertainty as a temporary inconvenience. It does treat it as a permanent constraint. Margins are built into calculations. Tolerance thresholds are explicit. System behavior under degraded conditions is documented. Contrast this with software systems that assume perfect network availability, infinite scalability, uniform hardware conditions. Those assumptions eventually fail. And when they do, systems collapse not because they were complex, but because their complexity was unaccounted for. The most stable systems, whether orbital or digital, share common traits. They're observable, redundant, tolerant of partial failure. They model uncertainty explicitly. They assume drift, latency, and variance as normal conditions. Space engineering succeeds because it aligns architecture with reality. Software engineering matures when it does the same. The goal is not to eliminate uncertainty. The goal is to build systems whose stability emerges despite it. In orbit, that mindset is non-negotiable. In software, it is becoming increasingly necessary. And perhaps the future of resilient systems lies not in controlling complexity, but in designing structures that remain coherent with it. So I hope that was interesting. I hope that, in a sense, compared those two different mindsets and emphasized the benefits of introducing uncertainty, unknown future directions, edge cases and everything else, and how systems on Earth can benefit from the same mindset and become more resilient and better in the long term, and as well more correct. So thank you for listening, and I hope you have a nice day. Take care.